All of you can give your attendance in the chat box. I repeat, those who have joined the class can give their attendance in the chat box. So it is around 1:14 p.m. I will not wait much time. Give me a minute so that I can present my screen. Can anyone respond whether my slides are visible or not?
Yes, sir.
Yes, sir. Yes, sir. Visible.
Okay, thank you. So let me start today from where we have left in the last class. If you remember, in the last class, we have started the Rayleigh-Ritz method. In the last class, we have started the Rayleigh-Ritz method. I have told you the entire procedure of Rayleigh-Ritz method, and then we have started solving one problem. We could not solve the problem completely. We could solve some part of the problem. So we will continue with that problem in today's class. That is this problem we have started. In this problem, if you remember in the last class, we have generated the potential of the problem in terms of integral equation, and our aim was to minimize this potential. In order to minimize the potential, first we have assumed a displacement field of the problem. From the diagram, it is very much clear that the chosen displacement field is polynomial function. So we have taken the higher order polynomial, that is the second order polynomial functions we have taken. Then we have computed the boundary conditions for this problem. That is, from the problem it is very much clear that the displacement will be 0 at the fixed end, that is u of 0 is equal to 0, and slope at the free end will be 0, that is du of dx at x equal to l will be 0, in which this u0 of 0 is your essential boundary condition, and du over dx at x equal to l is 0 is your natural boundary condition. And I have also told you in the last class that in Rayleigh-Ritz method, the chosen displacement field should satisfy the essential boundary conditions. It may or may not satisfy the natural boundary conditions. So what we did, we applied this essential boundary condition in the assumed displacement field, that is value of u is 0 when x is 0. When you put this boundary condition in equation number 5, you will get a0 is equal to 0. Then put this a0 in the assumed displacement field equation. Your displacement field equation becomes u of x, which is an approximated displacement field, so near about equal to a1x plus a2x square. Now you need to put this modified assumed displacement field in your potential of the problem. If you see the potential of the problem, there is a term called du over dx. That means you need to differentiate equation 6 with respect to x. If you differentiate equation 6 with respect to x, the value becomes a1, because d dx of x is 1, plus a2 into d dx of x square is 2x. So the value becomes du over dx as a1 plus 2a2 into x, which is equation number 7. So in place of du over dx, you have to put this value, that is a1 plus 2a2 into x, and in place of you have to put the assumed modified assumed displacement field, that is a1x plus a2x square. So if I guess we have solved this problem in the last class till equation number 7. If anyone can respond.
Yes, sir. Yes.
Okay, okay. So in the next step, what we need to do, we need to put all these values in the potential of the problem, and let us find out a simplified potential form of the problem after substituting all these values. So substitute the values of du over dx from equation number 7 and value of u of x from equation number 6 in equation number 4. Fine. So the resulting potential of the problem becomes pi is equal to half into EA integral 0 to L du over dx. Du over dx is a1 plus 2a2 into x. a1 plus 2a2 into x whole square, because it is du over dx whole square. So a1 plus 2a2 into x whole square dx minus integral 0 to L q naught into u is a1x plus a2x square into dx. Now we have to simplify this potential function. So let us simplify it. Pi is equal to half times of E into A, integral of 0 to L. This is of the form A plus B whole square. So I can write it as A square plus B square plus 2AB into dx minus Q naught is a constant quantity. Take it out from the integration. Integral of 0 to L A1x plus A2x square dx. So in the next step, just evaluate this integral, that is half e into a integral 0 to L a1 square plus 4a2 x square plus 4a1 a2 into x dx. Very easy. Just evaluate this integral. This is the value minus q naught into integral of 0 to L a1x plus a2x square dx. If you evaluate this integral, this is the value. Fine. The resulting value after the substitution of limits comes out to be pi is equal to half EA a1 square L plus 4 by 3 a2L cube plus 2 a1 a2L square minus q naught a1 by 2L square plus a2 by 3 L cube. So the resulting potential function for the problem after substituting du over dx and u in the modified form of potential function becomes pi is equal to ea by 2 in bracket a1 square L plus 4 by 3 a2 into L cube plus 2a1 a2 L square bracket close minus q naught a1 by 2 L square minus plus minus q naught a2 L cube by 3, which is equation number 8. This is the modified form of potential of the given problem in terms of unknown displacement coefficients a1 and a2. Is it clear? Equation number 8. Any doubt in this?
No, sir.
Okay. So let us move forward. So since we have found out the value of the potential function for the problem, then I know I have told you in the yesterday's class that Rayleigh-Ritz method, the main objective of Rayleigh-Ritz method is to minimize the potential of the problem. This is the potential of the problem. I want to minimize it. If I want to minimize it, then what I need to do? I need to partially differentiate. This is the procedure of minimization. You need to partially differentiate the potential function, that is pi, with respect to the unknown constants present in the potential function. If you see in this problem, there are how many unknown constants? A1 and A2. Two unknown constants are there. So two times I have to minimize this potential function pi. One, I have first time what I will do? First time I will minimize this pi by partially differentiating this pi with respect to A1, and then I will equate it to 0. I will get one equation. Second time I will partially differentiate this expression of pi with respect to A2, then I will again equate it to 0. So from this equation you will get, from this particular term you will get one equation, from this particular term you will get second equation. Both the equation will have the constants a1 and a2, so you are having two equations, two unknowns a1 and a2. You can easily find out the values of a1 and a2. Is the step clear?
Yes, sir.
Okay, so in the next step, minimization of potential function is done. What is I? I represent the number of unknown coefficient present in the final modified form of the potential function. If you see, this is my final modified form of potential function. And in this potential function, two unknown coefficients are present, a1 and a2. So this value of I will be, first time the value of I will be 1, second time the value of I will be 2. That means del pi by del a1 equal to 0. One time I will partially differentiate it, and second time del pi by del a2 equal to 0. So let us partially differentiate equation number 8 with respect to unknown constant a1. And you know that in partial differentiation, if I am partially differentiating any expression with a1, then I will only differentiate that equation in which a1 term is present. I will ignore the a2 term. So let us differentiate it. Del by del a1 into this expression, that is this particular expression, equal to 0. So I can write EA by 2, I can take it out common, del by del A1 of A1 square into L. So it will be 2A1L, 2A1L plus del by del A1 of 4 by 3 A2 square L cube. This I will not take because A2 is present. Then del by del A1 of 2A1 A2 L square. So it will be 2 times of A2 into L square, because del by del A1 of A1 is constant. So 2 types of A2 into L square, minus del by del A1 of this particular term. That means it will be Q naught L square by 2. Q naught L square by 2. Again, I will not take this term because in this term A2 is present. So this is the resulting equation after partial differentiation with respect to A1. I can bring this quantity to the right hand side. So it will become EA by 2 equal to 2A1 into L plus 2A2 L square equal to Q naught L square by 2. 2 cancel, and this particular L and this L get cancelled. So the resulting equation becomes, see, I am writing the entire equation in terms of A2. So the resulting equation becomes A2 is equal to Q naught by 2 times of EA minus A1 by L. Equation number 10. Is equation number 10 clear? Any doubt in this equation number 10?
No, sir.
Hello.
No, sir. No.
Okay. So I got equation number 10 in terms of, I have written A1 in terms of A2. Now, wait, somebody is joining. Okay. Now, second time, I will partially differentiate the potential of the function with respect to A2, and I will equate it to 0. Equation number 8 is my potential of the function. Now, I will differentiate partially equation number 8 with respect to the second unknown coefficient, that is a2. So del by del a2 of del a2 of your equation number 8, that is equation of pi, equal to 0. So partially differentiating equation 8 with respect to a2, that means I can take this ea by 2 outside the bracket, ea by 2 into I will not take this point expression, I will not take this one because a1 is present. Then del by del a2 of 4 by 3 into a2 square L cube. So it will be 4 by 3 into 2 times of a2 into L cube. This is the partial differentiation plus 2 times of a1 into L square minus, again I will not take this expression because I am partially differentiating with respect to a2. Then I will differentiate this expression, that is minus q naught L cube by 3 equal to 0. So you can take again this term to the right hand side. This is the final, this is that expression. So if you solve it further, your equation becomes 8 by, sorry, this equation, that is ea by 2 into 8 by 3 a square L cube plus 2 times of a1 L square equal to q naught L cube by 3. Now in this particular expression, if you put the value of a2 is nothing but equation number 10. In place of a2, just put this particular value, that is q naught by 2 times of ea minus a1 by L. Then the entire expression will be in terms of a1 and you can solve it and get the value of a1. And once you get the value of a1, you will put the value of a1 in equation number 10. You will get the value of a2. So let us substitute the value of a2 over here. If you substitute the values and if you solve it further, you will finally get the value of a1 coming out to be q naught into L divided by ea. So substitute this value of a1 in equation number 10, you will get the value of a2 and that value of a2 becomes, finally, that is minus q naught divided by 2ea. Value of a2 is minus q naught by 2ea and value of the unknown coefficient a1 is q naught into L by ea. Is the step clear?
Yes, sir.
Fine. I am not discussing these steps because these are simple mathematics. You have to factorize it. You have to take. You have to multiply. You have to divide. You have to add it. Fine. So I am not discussing these steps. Just solve it. You will get this value of a1 as well as the value of a2. So what I need to find out, I need to find out what? I need to find out the displacement of this bar as a function of x by this method. So I got the value of C1 and A1 and A2. So in order to find out the value of the displacement field, this is the displacement field. This is the assumed displacement field of the bar, that is a1x plus a2x square. I got the value of a1, I got the value of a2. Substitute the value of a1 and a2 in equation number 6. The resulting equation will be your displacement equation for that particular bar, which is valid for the entire domain of the bar, starting from x equal to 0 to x equal to L. So if you substitute the values of a2 and a1 in that modified assumed displacement field, the final displacement of the bar throughout its length is given by q naught upon 2ae in bracket 2lx minus x square. Is the problem clear?
Yes, sir.
Fine.
Haan, sir.
Simple problem is there. Only in Rayleigh-Ritz method, what you have to do initially first, see, governing differential equation as well as boundary conditions can be given. may not be given. In this question, I haven't given you the boundary conditions, neither I have given you the governing differential equations. But I know that if it is a problem of beam, that means if a beam is given to me and if a beam is bending, then this is the expression of strain energy and these are the expression for external work done W. Similarly, for a bar problem means along one direction displacement is happening, that is the bar. Then the value of strain energy is this expression and values of W will depend whether the point load is acting or traction force is acting or the body force is acting. Accordingly you will formulate the potential of the problem. Once the potential of the problem is formulated, you have to assume the displacement field of the problem. Displacement field can be polynomial function, it can be trigonometric function, but I know that the displacement field will be a trigonometric function in case of a beam because the beam bends and the bending pattern follow the sinusoidal curves or a cosine curve. Fine. So for that case, I have to take the displacement field to be the trigonometric function. Fine. And you have to choose the displacement field in such a way that it should always satisfy the essential boundary condition of the problem. Then what you need to do, you have to substitute the essential boundary condition so that you can find out any of the given unknown constant. You modify that assumed displacement field, then put the value of the assumed displacement field in the given equation of pi. That means you have to differentiate for this problem, you have to differentiate it one time, but for a beam problem you have to differentiate it two times, because for a beam problem the strain energy becomes half E into I integral over the entire domain d2u over dx2 whole square, second order derivative. And once you formulate the value of pi, then in that expression of pi you have to find out the values of, or you need to see that how many unknown constants or parameters are there. In this particular problem there are two unknown constants are present, that is a1 and a2. So the Rayleigh-Ritz statements tells that you have to minimize the value of pi by partially differentiating these unknown constant and then making it equal to 0. So for this case, since from equation number 8 it is very much clear that there are two unknown constant, so first time I will partially differentiate with respect to a1. Second time, I will partially differentiate this expression with respect to A2. If you solve these two equations, you will get the value of A1 and A2. Put the value of A1 and A2 in the given assumed trial solution or the displacement field, you will get the final displacement field of the problem in terms of x, and this displacement field is valid throughout the domain of the problem starting from x equal to 0 to x equal to L. That means you can predict the nature of displacement at each and every point of the bar due to application of the surface load Q naught. Clear?
Yes, sir.
Okay, so let us solve now. In the first problem, I made you solve the bar problem. In the second example, let us solve the beam problem. Let us solve the beam problem. Let us read the question. The question is a simply supported beam subjected to uniformly distributed load Q naught as shown in the figure. This is the UDL acting in the beam. Find out the deflection of the beam as a function of x. That means due to application of this load Q naught, the beam will deflect like this. This is the deflection. Say if you are talking about this point, at this point assume that the displacement is v1 at this, because at this point assume that the displacement is v2 at this point, assume that the displacement or the deflection is v3, That means this particular deflection is continuously varying with respect to the length of the beam. That means I can say that deflection of the bar is nothing but a function of x, and that is what we need to find it out. Secondly, the maximum deflection of the beam, what at which point the maximum deflection will take place and what will be the value of maximum deflection, that I need to find out. That is very much clear from the geometry that maximum deflection will take place at x equal to L by 2 due to symmetry. And lastly, the maximum bending moment induced in the beam. How to find out the value of maximum bending moment? We know that governing differential equation of moment is m is equal to E into I into d2 V, because here the displacement deflection is V, d2V by dx square. So once we got the value of V by this method, we will double differentiate it and then we will multiply it with the value of EI. We will get the moment, moment which is a function of x for the entire problem, how it is varying. And in order to get the maximum bending moment, that also from the diagram it is very much clear that maximum bending moment will take place when the value of x will be L by 2. So after finding the bending moment expression in terms of x, in that particular expression we will put x equal to L by 2 and we will get the maximum bending moment of the problem. Is the step clear what we will be going to do?
Yes, sir. Yes.
Fine. Okay.
Yes.
So, but before that, before starting the problem, see, in this problem, neither the governing differential equation of the problem is given to you, nor the natural and essential boundary conditions are given to you. So, can you find the boundary conditions of the problem by looking at the problem? By seeing this problem,
Sir,
can you
uh,
find out the boundary condition? I want the
so
essential boundary condition because
deflection at x is equals to 0 is 0.
that
0
means
to L by 2.
that means we can say that value of v, because v is the deflection
Yes, sir.
which is a function of x. That means value of v is equal to 0 when x is 0. Very much clear from the diagram. Okay, I
0
got
to x by 2,
one
sir.
condition. Second
L by
condition?
L by
Essential boundary condition is this.
Second condition is
So,
L by 2 when uh, the length is L x is equal to L by 2. The deflection will be maximum.
at x equal to L by 2 deflection is maximum, but see, I don't know the deflection yet. In order, I have to find out the deflection by this Rayleigh-Ritz method. In
Oh,
that I
okay, sir.
have to assume the
yes, yes.
deflection as some function, so I cannot take that boundary condition that deflection at middle point is maximum.
Okay, sir.
Sir,
Known
we have to
deflection,
take
known boundary condition from the problem. First boundary condition is known. What is the second known boundary condition from the problem?
sir x square by 2.
You can say that no, that you are coming, if you are telling about d2v by dx square, you are talking about the natural boundary condition, and Rayleigh-Ritz method strictly says that you cannot use natural boundary condition. Every time you have to go for essential boundary condition. So you tell me the second essential boundary condition of this problem. If you see deflection v, which is a
V
function of
is
x, will be 0 at x equal
L
to
L
L.
L. Yes, sir. मैं वही बताने वाला था.
Yes. So these are the two essential boundary condition which is present in the problem. You have to find it out, those boundary condition. If I give the boundary condition as well as the governing differential equation, problem becomes very simple. But don't expect that every time differential equation and governing, the governing differential equation and boundary conditions will be given to you. No, you have to find it out from the problem. Is it clear, these two boundary conditions?
Yes, sir. Clear, clear.
Then, in this method, after finding out the app or after assuming the deflection curve, after finding out the displacement field variable, which is a deflection, fine, I have to substitute these two boundary conditions to get the value of unknown constants. Fine, okay. So again in this method we have to assume a displacement field. Now can you tell me what is the nature of displacement field for this problem? Will it be a polynomial function or a metric function?
Sir, polynomial function, I think.
Polynomial function.
Polynomial function. How come it is polynomial? Because if this is your beam,
No, sir, it is a
displacement
trigonometric. It is a
is
bending.
varying like this. How come it is polynomial?
Oh, no, 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 sir. Yes, yes, trigonometric.
It has to be trigonometric. Polynomial means
Mm-hmm.
what? Polynomial is like this. This is a polynomial function, exponential function, cubic function, quadratic function. But if you see in this problem, due to UDL, the beam is bending in a sinusoidal kind of curve pattern. So if you take the, you can take the polynomial function, but the degree of accuracy will be very less. Fine. That means practically your solution is incorrect because you have taken the wrong assumed displacement field. So in this problem, the displacement field will be a polynomial function. But if you see in the last problem, due to this surface force Q naught, beam has a tendency to move. All its node and element has a tendency to move in along one direction. Here, the pattern is not a sinusoidal curve. Are you getting the difference between the first problem and the second problem? Hello.
Yes, sir.
Yes, sir,
Are you
yes,
finding
sir.
out the difference? So in
Yes,
this
sir.
problem, the displacement function will change. The displacement field will change. First step is very easy. You have to set up the potential of the problem. Potential is equal to the internal energy plus the external energy of the problem. Internal energy is nothing but the strain energy stored in the problem, and the external energy are those energies which are done by the external force on the problem, and that are taken to be negative throughout. So the equation of pi becomes pi is equal to u minus w. U is what? Strain energy. Formula will change. This is a case of, this is in this problem, bending of the beam is happening. In the last problem, the bar was displacing along one direction. So when the bending is happening, then the expression for strain energy becomes, see, for a beam problem, this is the equation of strain energy which I have to use. That is, U is equal to half E into I integral of d2y over dx2 whole square into dx. This is nothing but exactly the equation which you use in strength of material. If you remember, it is m square by 2 EI. I hope. That is the equation, m square by 2 EI in strength of material if you use. And you know that moment I can replace it by, I know that m is equal to EI into d2y by dx square. So in place
सर वो
of,
तो स्लोप का इक्वेशन है.
yeah,
स्लोप का इक्वेशन है एम
no,
स्क्वायर
moment
बाई
equation is
टू
this
ए.
equation. M is equal to E into I d2y by dx square. This is the equation, differential equation of moment.
हाँ ये वाला मालूम है. मैं स्लोप का बोल रहा था.
No, no, no. I'm not talking about slope. I'm talking about moment. So, but in strength of material, when you solve the problem for a bending of beam problem, if you find out the value of strain energy, that value I think near about comes out to be m square by 2 EI somewhat. M square by 2 EI. So we are converting this term by a differential factor and then integrating it over the entire domain. Ultimately, this equation and this equation both are same. The way of writing is different. Are you getting my point?
Yes, sir.
Fine. So, but see, in the last problem, we have used this equation to find out the value of strain energy because it was a bar problem. Bar was linearly varying along one direction. In the beam problem, bending is happening. So, the formula of strain energy changes. So, we will use this expression that is, yes, U is integral entire the complete domain. Domain varies from x equal to 0 to x equal to L half E into I d2V over dx2 whole square into dx. Let it be equation number 2. What is W? W is the external work done on this particular beam due to external load. And I have told you in the previous two classes while discussing the potential energy approach that this external work done is having three components. First component is work done due to traction force, which is nothing but a UDL, because we call UDL in FEM as a traction force. The second component of this external work done is the body force, which is nothing but the self weight of the beam or the bar, and the third component of W is the work done due to point load, that is work done, that is force into displacement U. So can you tell me for this particular problem which component I have to take in account to get the value of W? For this problem, which component of W will I use to get the value of W? Hello.
Sir, vertical component.
Vertical, no. You tell me in terms of whether I will take the traction component of force, or will I take the body component of force, or will I take the point load? This is the diagram. Tell me.
Sir, we can convert this into a point load.
So
That's not an
You
body,
issue.
body,
cannot
body,
convert. This is, see, FEM
body load.
is a real time problem. You, whatever the it is given to you, you have to take it as it is. You cannot convert. This is not a strength of material that you can convert it and you can solve it. You cannot convert it.
हाँ सर वही है मैं स्ट्रेंथ ऑफ मटेरियल का पॉइंट
No,
पूछ
no,
रहा
no.
हूँ
You cannot convert it. So which component will I take? If you see in the given problem, UDL is acting. Fine. And I told you that UDL is nothing but the traction force. So I have to take this traction force component to get the value of external work done. That also I know that yes, in potential energy approach, W is what? W is one component is the work done due to traction force, another component is the work done due to body force, and the third component is the work done due to point load. Since in my problem only UDL is acting, there is neither a point load nor the body force is acting, because nowhere in the problem it has been told to you that the self weight of the beam is something. Fine. So which equation I will use? I will use this first expression to get the value of W. Due to UDL, this is the work done. Here T will be replaced by Q naught and U will be replaced by V, because V is the displacement in my problem over the entire domain, and domain lies from x equal to 0 to x equal to L in negative direction. Is it clear?
Yes, sir.
Fine. So remember one thing in Rayleigh-Ritz method. See, value of U is always fixed. If you are taking a bar problem, whatever example we have did just now, that is the first problem, that will be the value of U. Always you have to integrate it like that. And for a beam problem, this will be the value of U. What will change? This W will change in each and every problem. You have to see the you have to read the wording of the problem, you have to read the diagram of the problem, and then you have to decide which component of W is given in the problem. Accordingly, you have to proceed. So from the diagram, I came to know that only the traction component is present, that is the UDL component is present. So the external work done on this beam will be due to this UDL, and that is nothing but minus times of integral x equal to 0 to x equal to L into the UDL component of force, that is Q naught, into the deflection of the beam, that is V of dx, equation number 3, which is W. Is it clear?
Yes, sir. Clear.
फाइन. अभी जब मैं नेक्स्ट प्रॉब्लम सॉल्व कराऊंगा, उस नेक्स्ट प्रॉब्लम में ना ही यूडीएल दिया हुआ है, ना ही बॉडी फोर्स दिया हुआ है, ओनली पॉइंट लोड दिया हुआ है. तब कैसे करेंगे सॉल्व? तो मैं एक एक वैरायटी आपको करा दूंगा, फिर बाकी का आप किताब से देख के सॉल्व कर सकते हो. फाइन, ओके. सो सब्स्टिट्यूट दिस सेकेंड एंड थर्ड इक्वेशन.
एक्सक्यूज मी सर.
यस
सर किताब का पीडीएफ भेज दीजिएगा सर.
I have already sent it. I have already sent one book in Google Classroom. SS Bhavi Katti.
Oh sir, I have not checked. Okay.
You can see, and by today also, or by 31st, I will send the soft copy of 2 more books. Okay, so just substitute the second and third equation in equation number 1. So the resulting potential function for this problem in integral form becomes x equal to 0 to x equal to L, half of EI d2v over dx square whole square into dx minus W, that is q integral x equal to 0 to x equal to L q naught into v dx. This is the final potential function of the problem, which is expressed in integral form. Is it clear so far? Hello?
Yes, sir.
Fine, okay. So can you tell me what is the next step? We have written the potential function of the problem. What is the next step? What is the next step? Next step is you have to assume the suitable value of this V, displacement. So from the diagram, I came to know that the displacement field will be a trigonometric function. Fine. So I can choose this expression, that is V of x is near about equal to, because we are approximating it, so I am not writing it equal to, I am writing it near about equal to. C1 is a constant, C1 into sine of pi x by L plus C2 into sine of 3 pi x by L. You can take much more value. This equation can be C1 sine pi x by L. First condition. Second condition, this equation can be C1 sine pi x by L plus C2 sine 3 pi x by L. The third condition can be, this equation can be C1 sine pi x by L plus C2 sine 3 pi x by L plus C3 sine 5 pi x by L plus dash 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 dash. If you increase the order of your displacement field, your solution will be much more accurate in nature. Is it clear? Any doubt? Hello? Any doubt so far?
No, sir.
Okay, fine. So this is my equation number 5. Fine. This is the assumed displacement field which I have chosen. That means by this method, I have to find out the unknown constant C1 and unknown constant C2. So before that, let us use the boundary conditions. We have the boundary conditions, that is V of 0 is equal to 0. Value of deflection will be 0 at x equal to 0. I know from the diagram. From the diagram again I know that value of deflection will be 0 at x equal to L. that is V of L is 0, and also the natural boundary condition which I know is that moment at the extreme two ends are 0. That means I can write moment is equal to E into I d2V over dx2 is 0 at x equal to 0, and EI d2V over dx2 is 0 at x equal to L. Yes or no? I can write these two equations of moments or not as a boundary condition.
Yes, sir.
Hello.
Yes, sir.
Okay. So, but I am not interested in these natural boundary conditions, but I am interested in this essential boundary condition. Now, if you put this essential boundary condition in equation number 5, fine. If you put this essential boundary condition in equation number 5, is the equation number 5 satisfied? Please let me know. If you put the essential boundary conditions in the assumed displacement field, is the equation number 5 satisfied? If it is satisfied, that means I have chosen the correct displacement field for this problem. If it is not satisfied, that means my displacement field which I have chosen is wrong. Please check it. That means value of displacement will be 0 when x 0. That means the value of v will be 0 when x is 0. When x is 0, when x is 0. So sine 0 is 0 plus sine of 3 pi. Sine of 3 pi is what? Because this is 0. 3 pi 0. Again sine of 0 is 0. So entire term is 0. So this boundary condition is satisfied. Now let us check the second boundary condition, that is value of this deflection is 0 when x is L. That means C1 sine of pi, in place of x write L. In place of this x write L. This L cancel, L cancel. Equation becomes 0 is equal to C1 sine of pi. Sine of pi is what? C1 sine pi plus C2 sine 3 pi. Sine pi is what? Hello.
Zero, sir. Zero, zero.
Sine pi is 0, sine 3 pi is 0. So ultimately, this Vx will be 0. That means the trial function or the assumed displacement field which I have chosen is correct. It is satisfying the essential boundary condition. So it is not like that by blindly I am choosing. You are choosing blindly the assumed displacement field, but you have to make sure that the essential boundary condition is satisfied or not. If it is satisfied, then it is fine. You can carry out the problem. But if it is not satisfied, then you have to modify your assumed displacement field. So it is done. Next is what? I will take 10 more minutes because this problem will take 10 more minutes to complete. Fine, then I will make you leave. Okay. Next is what I need to do. I need to evaluate or I need to substitute this particular value of assumed displacement field in the modified potential function of the problem. That means I have to differentiate this equation number 5 two times because it is d2v over dx x square. Then I have to take the square, and in place of v I will substitute this expression, that is c1 sine pi x by l plus c2 sine 3 pi x by l. So let us differentiate v two times with respect to x. If you differentiate it first time, it is equation number 6, c1 pi by l cos of pi x by l plus c2 3 pi by l cos of 3 pi x by l. Again, if you differentiate equation number 6, you will get d2v over dx2, and that equation comes out to be minus c1 pi square by l square into sine of pi x by L minus 9c2 pi square by L square into sine of 3 pi x by L. Now you can substitute this value of d2v over dx2 in the given potential function at this place, and you will substitute the value of v as C1 into sine pi x by L plus C2 into sine 3 pi x by L. Then you have to solve this potential function pi in terms of unknown constants C1 and C2. And I know from this, and then I have to see that potential function, that how many unknown constants are present. Accordingly, I have to minimize that potential function. Is it clear? Is it clear till equation number 7? Any doubt?
No, sir. No, sir.
Fine. So let us substitute the value of d2v over dx square and v in equation number 4. So once you substitute, this is the expression. This is the expression after substituting the value of d2v over dx square and v in the equation of potential. Now you need to do what? You need to integrate the entire expression. So before that, what you can do? You can take this term ei by 2 common outside the bracket. If you take it, it will become integral 0 to L C1. Fine. Then just differentiate. Fine. This is just integrate all these expressions. It is easy. I am not telling you because already you have done this kind of integration in mathematics. Just integrate the entire expression. Just integrate the entire expression. Once you integrate it, the final value of pi comes out to be yes, this equation number 8. The final value of pi comes out to be equation number 8, that is e into I pi to the power 4 by 4 into L to the power 4 C1 square plus 81 C2 square bracket close minus 2 Q naught L by pi C1 plus C2 by 3. Equation number 8. I know that I have skipped these steps, but these steps are simple integration which you already have did in mathematics. So I am not repeating those steps again. Is it clear? Any doubt in equation number 8? Hello? Hello?
No, sir.
Fine. Okay. So, and remember this value. This pi and this pi are not same. This pi is your 3.14 or 22 by 7. And what is this pi? This pi is the potential of the problem. So that's why, see, I have changed the symbol. I have written this pi somewhat like this. So make these things clear. Then you will tell that you can take pi common both ends, you will cancel out each other. No, this pi is potential of the problem, and this pi is your 22 by 7 or 3.14. So please keep this thing in mind. So if you see in this expression of pi, how many unknown constants are available? One is C1, another one is C2. So by Rayleigh-Ritz method, I have to minimize this expression of pi. Firstly by del pi by del C1 equal to 0, then by del pi by del C2 equal to 0. If you differentiate it, this equation number 8 partially by C1, fine, you will get the value of C1. That unknown constant value is 4 Q naught L to the power 5 by E into I pi to the power 5. In the second step, if you partially differentiate the potential of the problem by C2, you will get the unknown constant C2. and that value is coming out to be 4 q naught L to the power 5 by 243 EI into pi to the power 5. Is it clear? Any doubt? Any doubt in C1 and C2? Hello? Hello?
Sir, no doubt, sir.
Okay. So I got the value of C1 and C2. Then what I will do, I will substitute this value of C1 and C2 in my assumed displacement field, that is equation number 5. I will substitute the value of C1 as well as C2. I will get the deflection of the problem as a function of x for the entire problem, and that value comes out to be V of x is near about equal to 4 q naught L to the power 5 by E into I pi to the power 5 into sine of pi x by L plus 4 q naught L to the power 5 by 243 E into I pi to the power 5 sine of 3 pi x by L. That means the first part of the problem is done. That is deflection of the beam as a function of x. Fine. Next, we need to find out the value of maximum deflection of the beam. And from the diagram, it is very much clear that the maximum deflection will be at the center point of the beam. That means when the value of x will be L by 2. And sorry, hello, any doubt?
No, sir.
Sorry. Yes, maximum deflection. Sorry, maximum deflection means this V max I need to find out. I need to find out the value of V max. So, from the diagram, it is very much clear that the deflection will be maximum at the midpoint, that is at x equal to L by 2.
The
So,
center.
this is my this equation number 10 is my deflection of the beam for the entire problem. In this deflection function, put the value of x equal to L by 2 and then solve this x equation number 10. You will get the maximum deflection of the problem, that is q naught L to the power 5 by 76.82 times of EI. Is it clear? This is the maximum deflection of this problem.
Yes, sir. Clear.
Next, we need to find out the maximum bending moment of the problem also. So I know that bending moment at any section or at any point in the beam will be given by E into I d2v over dx2. So d2v over dx2 already we have found out. Fine. D2v over dx2 already we have found out in that expression
So you have to
of,
put the value.
yes, this is my d2v over dx2. Which one is my d2v? Yes, this expression, equation number 7. This is my d2v over dx2. In this expression, I will put x equal to L by 2. I will put x is equal to L by 2 and I will multiply it with E into I. If you solve it, you will get the value of maximum bending moment of the problem. And that maximum bending moment is coming out to be minus Q naught LQ by 8.05. Is the process clear? Any doubts?
Yes, sir. Clear.
Okay. Other people, please respond whether it is clear or not. Hello. Okay. I hope it is clear to all of you. So with this, I end the today's class over here. We will again meet in the next week with some more complicated problems. Fine. If anyone is left to give their attendance, you can give the attendance or else you can leave the meeting. Thank you.
Thank you, sir.
Hmm.
सर आपने जो बुक बोला है वो बुक फॉलो करने से होगा तो सर फॉर एग्जाम पर्पस?
You can follow that book, not an issue, but it will be better if you use that book also, which I have told you that in that book very precisely it is given. So, oh no, not an issue. You can follow this book, and I will try to send by this week 2, 3 more books. It is not like that in one single book you will find everything. You have to means found out the topics, and then you have to consult different books.
ओके
Okay,
सर, ओके.
fine. Okay, okay. Thank you.